Chapter 30 addendum is really just a summary of all the right-hand rules that we've seen in E&M. It's like, you know, right-hand rule central here. So we have a bunch of vector cross products. You know, starting with, let's start just 1A here. Force on a charged particle in an external B field. A positive charge moving, you know, to the right here like it shows, and then the magnetic field is down, then the force on the charge is into the page. And this is for positive charges, so if you have a negative charge moving in that direction, then the force would be in the opposite direction, right? Remember, for negative charges, you point your fingers in the direction of the velocity and then switch. Okay, so for current carrying wires, point your fingers in the direction of the current, cross in the direction of the magnetic field, and you get the direction of the force. For that top one, then, the force would be out of the page. For the other one, the current's going kind of up and to the right, the magnetic field is coming out of the page, and so the force is sort of down and to the right, mostly to the right a little bit. And even if you have a curved path, you go to the beginning and end points, and you're able to do the same thing we just did, but even for a curved path, because all the little segments add up, the vector segments add up. And so even for that one, the one on the top, the current is going in the same direction as the magnetic field, so there's no force, right? The right-hand rule doesn't work. Theta is 0 and sine of 0 is 0. But for the other one, you've got, again, the current going kind of to the right and up a little bit, and the magnetic field coming out of the page, so the force is sort of down and to the right, perpendicular to that length. 1C, when we have two wires next to each other, how does that produce a force? Again, if you're going to do this, where you're drawing out the magnetic fields and all that stuff, it's just review. You would put your, fingers in the direction of the current, and that tells you the direction of the magnetic field. You can draw that on the other wire, and then put your hand in the direction of the current. So for the top one, the forces are towards each other. For the bottom one, the forces are away from each other. All right. If you have a magnetic dipole created by a current loop, the loop on the left, right, that square thing, as the current is going around, the magnetic field is pointing out of the page. For the other one, though, where the current is going clockwise, right, you can put your fingers in the direction, then you've got the magnetic field going into the page. Okay, and then we also have the dipole moment mu, right? Okay, so torque on a current loop. If you have current going around, like on the left, if you put your fingers in the direction, so the left loop, if you go all the way to the left, the current's going down, the magnetic field is to the side, so the force is going to be out of the page. And on the right side of that loop, the force is going to be into the page because you put your fingers in the direction of the current, magnetic field is to the right, and then it's going to be down. So it's going to turn where the left side is going to be coming up towards us. That's the torque. Whether it turns or not depends on the other motion. Whereas the loop on the right, if the magnetic field is into the page, you can find the force on each of the wires, the top, bottom, middle, left, and right, and all the forces cancel out. There's no turn at all. Okay. Let's see. Magnetic field at a point P due to moving charges or current. Right. So for the left, you would draw, the magnetic field down and to the right would be going into the page, and on the left would be coming out of the page. Based on the direction of the current for this loop, right, or this arc, all the other straight wires are 0 because they're lined up with that point. But from the arc, if you point your fingers in the direction, your thumb in the direction of the current, then you see that at point P, the magnetic field is into the page. Okay, for a solenoid, here you've got current going around, right, where it's coming down in front. And so you put your fingers in the direction of coming down in front, and that tells you that the magnetic field is pointing through the right of this thing. And if I take that and I make a toroid out of it, the special treat at the end of the year, by the way, or at the end of this unit, is that we do Duncan toroids, where you tell me the type of donut, I'll bring it in. It's got to be a toroidal donut. And then I give you little licorice loops. And you're going to make a toroid out of it, and you're going to indicate the direction of the current or of the magnetic field. And it's just really simple. That's it. And then you get to eat the Duncan toroid and the candy. So anyway, but for this one, if you've got the current coming up on the outside, then again you can point your fingers in the direction, your thumb in that direction, and your other fingers are pointing in the direction of the magnetic field on the inside, and so that's producing a current, or an Amperian loop. Or the Amperian loop is what we use to evaluate the current in the magnetic field. You see the magnetic field is pointing clockwise. Current induced in a coil due to a changing magnetic flux. Again, this one, Lenz's law, the idea that the current is induced to oppose the change in magnetic field. So if I have an increasing B into the page, right, it's into the page, it's increasing, then I'm going to want current to create a magnetic field in the opposite direction, so that's up out of the page, and so it's going to create a counterclockwise current. If it's into the page and it's decreasing, then I'm going to want a current to create a magnetic field into the page, and so that's going to create a clockwise magnetic field. All right. That's really it. And so I'm going to do this and the last packet, chapter 31, in the same lecture, because chapter 31 is very brief here as well. Most of what we're doing here is we're just looking at concepts. We're not looking so much at what do we call it? Quantitative analysis. You see there are even very few, even no examples. And so if I have, now I'm looking at the last type of non-steady state circuit, an LC circuit or an oscillating circuit. Okay. So if I have some inductor in series with a capacitor, say I charge up this capacitor, okay, and then I connect it to the inductor and release it from the battery, what's going to happen? This thing is going to want to discharge, right? And so it's going to discharge, it's going to create a current. When it creates a current, that's going to create a magnetic field in here, right? Changing current is going to create a magnetic field, and then, or the current will create a magnetic field, and then once this is totally discharged, the current will want to stop. However, this is going to maintain the current, it's going to keep the current going until this thing discharges, but when this thing is discharging, it's going to charge this back up. And so then I'm going to have plus and minus here. This gets charged up now, it wants to discharge. And so what we end up having is an oscillation. We have an oscillation between the magnetic field in the inductor and the electric field in the capacitor. And we get simple harmonic motion here. And you can see the derivation there, where using Kirchhoff's law, 1 over C times Q, so that's, Q equals CV, so this is the EMF on here, is equal to plus L d squared Q over dt squared. So that's the derivative of the current, and current is the time derivative of the changing charge, so that's 0. Okay. So what we end up with, if we look at this is actually simple harmonic motion. This fits our description of simple harmonic motion, and so we end up with charge as a function of time is the total charge times cosine of omega t plus phi. Simple harmonic motion. The current then is the derivative of this, so we end up with d dt. All right, let me just write it. Negative omega q sine omega t plus phi. Okay. Now the really cool thing here is that this is going to have some frequency at which it oscillates. If then you can, say, direct at this some electromagnetic pulse that happens to match the frequency, then you end up with resonance. Right? And all you need is some external source of electromagnetic waves, and you get resonance happening here. That's how radios work. Right? When someone builds a radio, all they're really doing is they've got an output source where they can have a speaker or something, but this is it. You tune the radio by changing the capacitance and the inductance to match the frequency of the wave. And so you don't need a battery or anything else. All you need is something like this, because those waves are already in the air. That's a pretty amazing thing, and that's one of your optional projects if you stick around during the time after the exam. Okay, Rlc circuit. This is the last type of circuit where we plug a resistor in here. What does adding a resistor do? It decreases the energy over time because that resistor now is going to heat up, and so we get power dissipating over time as it goes back and forth. And you have to know what these graphs look like, but we're not going to do calculations with this. So you've got the oscillating current back and forth, but over time it's decreasing. Okay, that resistor is going to decrease the amount of energy in there. Some different types of magnetic materials. There's ferromagnetism. Ferromagnets are things like iron where they don't have a magnetic field of their own, but you can induce a magnetic field in the material. Diamagnetism, these are most common materials, including humans. As a matter of fact, there was a scientist who suspended a frog in a magnetic field, a very strong magnetic field, and you can look that up. I think Andre Geim is the name of the scientist, because even frogs are diamagnetic materials, where there's a very weak magnetic dipole produced in the atoms inside an external magnetic field. And paramagnetism, these have a net magnetic dipole moment even in the absence of a magnetic field, and when they're placed in a non-uniform magnetic field, they will move toward the region where the magnetic field is stronger. Okay, so E&M equations. The final summary of this whole thing is what we end up with: Maxwell's equations. And Maxwell's equations are a summary of everything in E&M. And because they're so simple, it's just these 4 equations, and if you know the calculus behind them, they are pretty simple. Einstein, when he saw these, he said they were the most beautiful thing he had ever seen at that point. And so it's Faraday's law of induction. Right? So this has to do with an induced electric field as a result of a changing magnetic field. Maxwell's law of induction. So this is getting a net magnetic field as a result of a changing electric field. Right? And this is how electromagnetic waves work. The Ampere Maxwell Law, which we looked at, it's like where you have a magnetic field produced by a changing electric flux, plus mu naught times any enclosed current. And then displacement current, so this is where a change in the electric flux is equal to I over epsilon naught. And so those are the E&M equations. The Maxwell's equations are on the next page, and this is Gauss's law for magnetic fields, and then Faraday's law, which we just looked at, and then the Ampere Maxwell law, which has to do with getting a magnetic field as a result of some enclosed current or changing electric flux. And let's see what's on this last page. And then again, just a page about Maxwell's laws. And that's it. That's the entire course.